Okay, so here's another stupid idea. I need to talk about stupid ideas to then kind of introduce how non-stupid the next ideas could be. So another stupid idea is to expand. It's not a stupid idea actually in general. It's a very smart idea. Is to expand the representation to a higher dimension by expanding it on a set of basis functions. So imagine, for example, that your input variable is a scalar. You just have one x, okay, one scalar variable x, and you'd like to approximate a function of x. It's a nonlinear function of x, okay? Say do regression, approximate a curve. So a linear function of x only has two parameters, and the only thing it can do is fit a line. It's just linear regression in one dimension. But if you have kind of a wiggly curve, one thing you can do is you can place a whole bunch of bumps along the x-axis, okay, where a bump is a function called phi here, phi of x. Each phi is a bump placed at a different location. And now you can sort of convince yourself visually that with a linear combination of those basis functions, you can pretty much approximate any wiggly line you want. If you put enough of those bumps close enough and they're kind of narrow enough, you can always find a linear combination of those bumps that will kind of approximate a function just about as close as you want if you make the bump as close as necessary. Okay, so that sounds like a great idea, except it's got the same problem as the polynomial thing, which is that it blows up with dimensionality. That's the curse of dimensionality. So if you want to put bumps on the space, you want to tile an n-dimensional space with bumps, and you have k bumps in every dimension, then you need k to the n bumps to cover the space. Doesn't sound like fun because n can be very large. So it's not entirely practical for that reason. Okay, but then you might realize, okay, we talked about this idea that faces lie in a low-dimensional space, in a high-dimensional space of stuff. So, you know, if I take pictures with 40,000 pixels, say, you know, 200 by 200, within the and I want to do, say, face recognition, or face detection, in the space of all possible 40,000 dimensional vectors, the actual images that I will observe will occupy a very small portion of that space. So what I could do is only put bumps at the location where I actually have data, right? And in particular, what I can do, which is kind of the next less stupid thing, instead of tiling the entire space with bumps, I'm only going to put bumps wherever I have training samples. So I'm going to put one bump around every single training sample. Okay, it doesn't matter what the shape of the bump is. I'm going to put one bump around every training samples. Okay, so if I have p training samples, now I just need to compute a linear combination of p variables, which is the value, the height of the bump at any particular x vector that I have. Okay, so you could think of this as a two-layer system where I feed the x vector, I compute the height of the bump at a whole bunch of xi location. Those xi here indicate the location of the bump, if you want. K is the bump function. Okay, and again, this could be any shape. And so what I get out of this is a p-dimensional vector, which are the height of the bumps at x, knowing that all the bumps are centered on all the training samples. Okay, I have to adjust the width of the bump so that, I mean, they don't actually have to be bumps. They could be parabolas. They could be all kinds of stuff. But you know, let's imagine, for the sake of simplicity, that they are what's called a radial basis function, a kind of bump that's isotropic. So now I've transformed the problem of a linear classifier in n dimension into a linear classifier in p dimensions, where p is the number of samples that I have. And I know for a fact that if the bump are narrow enough, I'm always going to be able to get the correct answer on the training set. Okay, so if I made the bump narrow enough so that they don't interfere with each other, whenever I put an x vector here, only one bump is going to be non-zero. All the bumps are going to be 0 except 1, which is the one under which x is. If the bumps are too narrow, of course, I could be outside. But if it's a training sample, I'm going to be right in the center of one of the bumps, right? So the vector I'm going to get here is going to be 0, 0, 0, 0, some large value 0, 0, 0, 0. Large value being the top of the bump. Let's say 1. Okay. So by simply writing the answer I want in the weight that comes out of this bump, I can get the answer I want. Okay. So I can get 0 error on the training set here by doing this trick. And in fact, that's the kernel trick. So if you guys have heard about supervector machines, that's what a supervector machine is. I'm not going to go into the theory of this, because you're going to hear about this in the other machine learning course, David Zontag's course, which many of you, I think, for many of you, that's a required course, so maybe not everybody. So I'm not going to go into the theory of kernel methods. But the basic idea is that, essentially, you put a bump around every training samples, and that allows you to basically nail the training set with 0 error, essentially. And with a bit of regularization of this linear classifier, and by varying the width of the bump, you can get some good generalization properties. Okay? So you could think of now this first layer here. So what we have now is a 2-layer system, a feature extraction or some sort of feature extraction. You can think of it as feature extraction that kind of measures the similarity between the input vector and every training sample or a subset of training samples. It's a subset if some of those weights are 0 at the end. And the second layer is the linear classification. Okay, so the only manual design thing that we have to do here is decide on the k function, the kernel function, the similarity function that we use to compare the input vector to an example. Okay, it's actually a pretty big deal to come up with a good kernel function, but that's the only thing we need to do. Other than that, this feature extractor trains itself, and it is trained in a way because it uses the training set to build those bumps. Okay, it's trained in an unsupervised manner because it doesn't require to use the labels to be trained. Okay, so the training algorithm for this layer is very simple. Collect all the x vectors from your training set and put one bump around each of them. You don't need to use the labels. Okay, so it's unsupervised in that sense. And then the supervised part is the linear classifier on top. Yes? Right, okay, so in practice, when people use things like kernel machines or supervector machines to do image recognition, they don't do it on the pixels. They have another feature extractor before that turns the pixels into a suitable X, okay? But here, what I'm talking about is I'm kind of building up a series of techniques that will allow us to learn the entire thing from end to end. So in pretty much all of examples we're going to talk about in this class, X is actually the raw data. Pixels, time frequency representations for speech, some sort of representation for language, things like this. It's sort of as low level as possible. Because the whole principle is that we're going to learn the whole thing, right? But if you want to use kernel machines, you're going to have to use handcrafted feature extractors beforehand because they're not going to work on raw pixels. Okay. So I just want to mention very briefly, just to put things in perspective, even though this is not the topic of this course, that this kernel idea of comparing samples with each other with a kernel function actually allows you to do things like polynomial classifiers in very high dimension without paying an exponential price. Okay, so that's the cool thing about this. This is why a lot of people 20 years ago got really excited about supervector machines, because it allows you to learn discriminative surfaces that are as complicated as high-degree polynomials or even more complicated things than this without paying the price computationally. So instead of having, you know, an exponential number of bumps, you just need as many bumps as you have training samples, and then you can prove that you can approximate just about anything with this. And here's a very quick example here for degree 2 polynomial classifier. So, it's based on a result analysis that says that if a kernel satisfies the Mercer condition, then you can view this kernel as a computation of a dot product in a high-dimensional space of features phi of x. So the dot product between phi of x and phi of x prime is equal to the application of the kernel function to x and x prime if k is a so-called Mercer kernel. And Mercer kernels are those for which this k matrix is symmetric and positive definite or positive semi-definite. So replacing this dot product in high-dimensional space by a kernel function is called the kernel trick. And there's a lot of algorithms that you can reduce to a set of dot products, and whenever you have dot products, you replace it with a kernel function, and you can claim that what your kernel function actually does is a dot product in the super high-dimensional space, possibly infinite dimensional. And there's cool math to do around this, which is what people get excited about. So here's an example. Let's say our phi function, phi of x, is something like this that is very similar to what I was telling you about earlier, where we map the components of x to 1, square root of 2x1, square root of 2x2, square root of 2x1 times x2, x1 squared, x2 squared. Then when you compute the dot product between two vectors mapped through this phi function, you can convince yourself by just doing the calculation that this reduces to x dot x prime, so dot product between x and x prime, plus 1 squared. Okay, so this very simple calculation here is equivalent to doing a dot product in this degree 2 expanded thing, and that's valid for any number of input dimensions. Doesn't matter what the dimension of x is. So of course we're never going to compute this because that requires computing this large vector. We're always going to go through that. And we're going to try to reduce all our algorithms to a set of dot products. That's the basic idea of kernel machines. And in fact, you can generalize this to any polynomial expansion of any degree. Basically, it reduces to this expression here, x dot x prime plus 1 to the power d. One kernel that people use a lot is the Gaussian bump. So it's another bump function, one of those bump functions that happens to be like a Gaussian for radial basis functions. Okay, so it's a bit of magic. It's basically a piece of math that tells you, okay, you want to compute a polynomial surface in a high dimension, but the only thing you care about is the value of this function over p points. Then you don't actually need to do this. You can just do a bunch of dot products in p dimension. Compute p dot products in n dimension, and you're done. Just this operation. Okay, so now if you think about what a support vector machine type, kernel machine type expansion does, is that it turns your input vector into a high dimensional vector of p dimensions, which generally is kind of sparse. So if you have those Gaussian bumps, many of the bumps are going to have very, very small values. Because if you have a Gaussian bump, if x is outside of that bump, the value of the bump is almost 0, right? So the vector is going to be full of very, very small values, mostly almost 0. And then a few of them are going to be large. That's called a sparse vector. And the concept of high-dimensional sparse representation is going to come back a lot during this course. Okay, next idea. This is going to connect. Who has never heard of k-means clustering? Okay, you're going to have to learn about it. I'm not going to explain it, okay? It's very simple. The algorithm is 3 lines, but you need to know that. So some people could say, well, okay, I can have p bumps in my space to do this expansion, But a lot of those bumps, many training samples are very close to each other. Why do I need, many bumps when I have a whole kind of bunch of samples that are very near each other? Maybe I can use only one bump for all of those samples because they're all from the same class, so I don't need to be able to discriminate between them. I just want to use one bump for that cluster of samples. And so a simple way of doing this is to run the k-means clustering algorithm, right? Take all your x points from your training sample, run a k-means clustering algorithm on this, or a mixture of Gaussian algorithm. If you don't know what that is, doesn't matter. Let's say k-means. So k-means gives you k prototypes in such a way that the average distance between any point and its closest prototype is minimized. Okay, the square distance is minimized. Summed over all the training samples. So now you use those k points as the centers of your bumps. Okay, all the theorems about kernel machines go out the window, but that doesn't necessarily mean that it doesn't work. Okay, it just means that maybe we don't have the right theorems. So that allows you to reduce the number of bumps perhaps by a considerable amount. Okay, so that's the basic idea. Very, very much the same architecture as before. We take an X vector, we apply a bunch of bump functions to it, where the bump functions are placed in various locations in the input space, and those locations are determined by k-means clustering. Okay, so we have k of those guys, and then we stick our linear classifier on top. Yes? Well, so that's the danger. The danger is that you might cluster things together even though they are in different classes. And in that case, this idea is not going to work. And what you would need to do in that case would be to increase k, or to use some other technique. Okay. There's another set of techniques you can use also, which involves using the labels to train the k. Or there's yet another idea, which is that you pre-train with k-means, and then you fine-tune in a supervised manner. You use this as a neural net, and you fine-tune it with gradient descent. We'll talk about this next. I mean, later. Okay, here is yet another idea. That looks even more stupid. It's random projections. But it turns out there are theorems that suggest that in some cases this is actually not such a stupid idea. Basically, you take your x vector and you compute the dot product of this x vector with a whole bunch of random vectors. Okay, let's go random projections. And so it's as if you were taking your vector and projecting it on a whole bunch of lines, essentially. And then what you get is the length of the projection on that line. Then you transform those projections into with some nonlinear function, again, because it has to be a nonlinear transformation, otherwise it doesn't do anything for you. Let's say a threshold. Okay, so if the dot product is larger than the threshold, you set it to 1. If it's lower than the threshold, set it to -1. And then you stick your favorite linear classifier on top. Okay. There are a few things for which this might work, but for complex problems, you're not going to recognize objects with this. This isn't going to work for that. But there are theorems that tell you that if you have p points in n dimension, then with log n, order log n times the coefficient projections, you pretty much get all the information there is to get about all the points. It's called the Johnson-Millenstrass theorem. I'm not going to state it in any detail, but there's this idea that in high-dimensional spaces, we have a bunch of points. The pairwise distances between points are preserved with a lower dimensional representation of the points generated by random projections. Okay, let me go back to the reason why you need this transformation to be nonlinear. Imagine the feature extraction here were linear. Okay. Now, when we plug our linear classifier on top, what we get is so basically if the first layer is linear, you can think of it as a matrix, right? Multiply the input vector by a matrix, you get another vector. Then you multiply this by the weight vector to get the dot product. And so the overall operation is the product of a matrix by a vector, transpose. And that's a vector. The product of linear operation is still linear. So you haven't done anything by adding another layer. It's just another linear operation that just consumes a huge amount of computation for nothing. Okay? So it has to be nonlinear. Okay? And in fact, that's something we're going to see again in the rest of the course. As we're going to go, we're going to add layers to those those models. Here we're talking only about two-layer systems. But what it becomes interesting when you start adding more than that and trying to figure out how to train all those layers. And all of those layers have to be nonlinear. A linear layer doesn't really count. Because you can always collapse it with the next layer. Yes? Okay, so I didn't actually say that the vectors with which you compute the dot product are not the training samples. They are random vectors. Okay. Oh, it's the same set for every training example. Yeah, you fix once, you draw the random vectors once, and then you just work with them. So as a matter of fact, the very early perceptrons were exactly like that. They were threshold linear functions, so linear combinations followed by threshold with random connections. The big spaghetti plate that you saw in the perceptron, the feature extractor, is actually random connections. So you have units that combine random subsets of pixels with random weights. I mean, they're binary weights, actually, +1, -1, with a threshold. That's actually called a gamma perceptron or gamma perceptron, where the two layers actually are threshold units. So this is going back to the 50s, right? People didn't know what else to do. That's what they did. Okay, but the next idea, and the root of deep learning, really, at least for supervised model, is to say, well, if I map X to a bunch of units that each take the dot product with a weight vector, okay? So same as the previous example with random projection. But then I map those to continuous functions. Then what I could do possibly is actually learn the weight vectors for the first layer, because the function I mapped from here to here is now differentiable. Okay? So because it's differentiable, I can figure out which way to adjust those weight vectors so that I get the answer I want at the output. I can adjust not just those weights, but also those guys, because I can figure out the gradient of whatever loss function I want to minimize with respect to those weights, given that they go through a continuous function, a differentiable function here. That's the basic idea of multi-layer neural nets and the backpropagation algorithm. Which I'm not going to talk about today. Okay, so now going back to, let me actually go back to this. Okay, before I forget, I'm gonna tell you, because the question was just asked. Despite what Albert says, the class begins at 5:10 and ends at 7. Okay. I'm told Albert says it begins at 4:50, but no, it's 5:10. At least that's what administration of data science tells me. Okay, so now if we kind of forget about the 50s and 60s and even the 90s and project ourselves in the mid-2000s, okay, so slightly more recent, less than 10 years ago, what people actually use for pattern recognition is slightly more sophisticated, and there's this two-layer approach of feature extraction and classification. really, most of the systems actually have 3 stages in them. And these were kind of the dominant approaches until very recently, basically until deep learning kind of, replaced this. So for speech recognition, the architecture that people would use would be something like a handcrafted feature extractor that turns the raw speech signal into a sequence of vectors. Typically, the vectors would have anywhere between 12 and 50 dimensions, something like that order of magnitude. And we get one of those vectors for every 10 milliseconds of speech. Okay, so about 100 times a second, you get a 40-dimensional vector or so. Okay, and so these are handcrafted features. So this is 40 dimensions. Typically, a system that tries to do acoustic modeling in speech recognition attempts to takes a few of those vectors, successive vectors, each representing 10 milliseconds of speech, or shifted by 10 milliseconds. They actually represent more like 25 milliseconds, and tries to map this short sequence of vectors, typically 3 or 4, into a probability distribution over categories of sounds called phones or subphones. So what is a phone? So we all know what a phoneme is. Okay, so A is a phoneme. Oi is a phoneme. It's a diphthong because it's got 2 sounds in it. Pa is a phoneme. But the sound in the P sound in Pa is a phone. Okay, and then you could divide this phone into kind of little pieces, and those are called subphones. And then for the sound P, there is all kinds of different categories of subphones depending on whether the P is surrounded by, say, preceded by O and followed by A, or some other things that surround it. These are called context-dependent subphones, or context-dependent phones, but you have subphones within those things. And typically, typical human language, when you try to reduce it to categories like that are elementary sounds, depending on what context they appear in, that are very short, you get anywhere between 3,000 and 8,000 categories. Okay, and those are somewhat arbitrary categories. They're not categories that humans can easily identify, but they are sort of artificially created by the process that comes after this, called a hidden Markov model. So I'm not going to explain just now what it is, but the hidden Markov model essentially has 3,000 or 8,000 states in it, and each state represents one of those context-dependent subphones. And what the acoustic modeling system has to do is map a little window of 10 milliseconds of speech into one of those, into a distribution over those 3,000 or 8,000 categories. Okay. So it's a classification problem, where the input dimension is on the order of 100 or so. So, anywhere between 40 and a few hundred, depending on how many of those acoustic frames you take. And the number of categories at the output is 3,000 or 8,000. Now, you guys have all played with logistic regression, right? And presumably you've played with multinomial logistic regression, so multi-category classification. And basically what those acoustic modeling systems do is that at the end, the last layer you could think of as a multinomial logistic regression. Okay? But before that, it's something else. So classically, you have this MFCC feature extractor, and then the next layer up is very similar to this idea of bumps trained with k-means, except they're not trained with k-means, they're trained with mixture Gaussians, which is kind of soft k-means, if you want, but for a practical purpose. So I don't know if you guys from the data science program have studied mixture Gaussians. I actually didn't check the syllabus for intro to data science. No, you haven't talked about this, right? I mean, you'll hear about it in the other course, but you don't need to know exactly what it is. Essentially, it's kind of like k-means, except it's soft. So instead of, every point being assigned to a single prototype, it is kind of a soft assignment to a point to the nearest prototypes depending on the distance, essentially. Oops. And so essentially what this does is that it turns this 40-dimensional or 100-dimensional vector into a very high-dimensional vector, typically 10,000, 20,000, actually quite large, which are the height of 20,000 bumps, where the bumps are obtained with essentially what amounts to k-means, or kind of a refined version of k-means, if you like. In fact, the position of those bumps are kind of adjusted using the labels, but I'll tell you about this later. And then essentially what's on top of this is multinomial logistic regression, a linear classifier, a multi-class linear classifier that uses multinomial logistic regression. Okay, so that's classical acoustic modeling and speech recognition. Classical method for object recognition in images until about last year. Okay, it changed really recently. So until last year, this was the dominant approach to object recognition. And last year, deep learning methods, convolutional nets, namely, won a competition called the ImageNet competition by a huge margin over those methods, and all of a sudden everybody switched to these new methods. So the basic idea here is very similar to the one on top. You have handcrafted features that are fixed, either the shift invariant feature transform or the histogram of analytic gradients. What those features do is that they take a patch in the image, and then they figure out if the edges within this patch are oriented vertically or sideways or horizontally, and you get a vector that represents kind of a histogram of how many edges within this patch region are in each direction. Okay, so it's kind of a histogram of orientations within a region. Both of these guys do this in slightly different ways. Okay. Typically, for a 16 by 16 or 64 by 64 patch, you get a feature vector representing those histogram orientations of size 128 or so. And you apply this at every location in the image. Okay, so for every patch in the image, you get the distribution of edges. And then for every location, this 128-dimensional feature at every location, again, you map it to a high-dimensional space using k-means or sparse coding or mixture Gaussian. Sparse coding is another way of obtaining a nonlinear transform of a vector into a high-dimensional space where most of the components are 0. And we'll talk about this at length, okay, later. So this is unsupervised, again. Then very often there is a pooling operation here which consists in computing the average of a bunch of vectors like this that come out at every location. And then you feed this average vector to a linear classifier, say a support vector machine or multinomial logistic regression, doesn't make much difference. Okay, the modern implementations of this until last year use something else here, a kind of a smart pooling which allow things to move within an object, but these are kind of details. Yes. So pooling is, okay, so what you get out of this, you can think of it as a 3D array, right? For every location on the image, you get a 128 feature vector. Okay, so it's 2D because of the image. You get one of those vectors for every location, and the third dimension is the 128. Okay, when you pass this through that, you also get a 3D kind of array where, the first two dimensions are spatial, and then the other dimension is how many of those, what k is here, how many of those prototypes you have, what the size of each vector is, and it's typically in the thousands. Okay. So here you get, for a whole image, you get a whole bunch of 4,000 dimensional vectors, let's say, at one for each location every few pixels from the input. And very often what people do is to just compute the average of all those 4,000 dimensional vectors. So you get one single 4,000 dimensional vector now. And the reason for doing this is that now if I move the input image a little bit, that average is not going to change very much. Okay? So it's a way to build shift invariance into the system. Okay, that's the basic idea of pooling. Again, we'll talk about this at length when we talk about convolutional nets. It's an old idea. this idea actually has its roots in neuroscience, not in computer science or engineering. In fact, what people do is not average all the pixels in one, I mean all the feature vectors into one. Very often the image is cut into sections and the average are taken over each section, so you get kind of a collection of those vectors, not just one, for each location. Do you have a question? You average over over space, yes, exactly. It's spatial pruning. Okay, so what we're going to do with deep learning is something slightly different, and I'm just going to give you a taste of it because there's 5 minutes left. But basically, we're going to attempt to figure out learning algorithms that will allow us to train a whole hierarchy of modules, and each module is going to turn whatever comes into it into a slightly more abstract, higher level representation where irrelevant variations of the input are eliminated, and the useful information for classification is preserved. Okay. So here I've used some visualization that were produced by Matt Ziller and Rob Fergus in our lab. So Rob is a professor here who some of you might have taken a course with him, and Matt Ziller is a former student of his. And they built a deep convolutional net very similar to the one I showed in my demo, which has actually many more levels than this. It has something like 10 levels. And what they did was kind of try to visualize. So it's a giant network where it has many variables that are computed all the way. What they try to do is visualize what particular input pattern will maximally activate a particular detector in that whole system, depending on the layer. And what you see in those systems is that the low-level feature detectors, essentially, once you train it, so this system was trained in an entirely supervised manner, using stochastic gradient descent, using the backpropagation learning algorithm, which I'll tell you about a lot over the next few weeks. And what the system ends up learning are detectors for low-level features like this. So the first stage, the first level of feature extraction, if you want, ends up learning to detect things like oriented edges in the image, the various orientations, and contrast of particular colors at various orientations, and things like that. Okay, these are spontaneously trained by the system if you train it on, a few million images. Yes. Okay, yes. So it's not actually exactly that, but it's a good approximation to that. So there's a good approximation of a pixel configuration on a local patch in the image that would maximally activate the detector, the feature, if you want, at the first stage. Okay, but not exactly. It's actually kind of a reconstruction, and so it's not exactly similar to an input, but it's a pretty good approximation. Basically, those are like filters. So those are like kind of, think of each pixel here as 3 values in RGB. Okay, and think of each of those squares here as a vector, which in this case has 7 by 7 by 3 values. You compute the dot product of this vector with the patch from the image that's underneath it. And if the patch that's underneath the image looks like this, then the corresponding output is going to be maximally activated. So it's a little more complicated to do this for the following layers, but you can do similar visualizations. So let's see, what is it? So this guy, for example, is a couple layers up, and those are sort of examples from the training set that maximally activate a particular detector, in the 3rd layer or something like this. So you start to see motifs like circles and corners and gratings and various textures, etc. And then a couple more layers up, you start to see kind of parts of objects and kind of distinctive features and heads of birds and things like that. It's a bit of a cheat here in the sense that these are actually taken from the training set if you want. So it's taking an example from the training set and among all possible things from the training set, seeing which one maximally activates a unit and then trying to reconstruct it. And so you get something that looks very much like an example from the training set. And so, but it's kind of a way of giving you an idea of how more abstract the feature detectors are as you go up the layers. 10 or 12, I can't remember. Depends on what you count as a layer or not, because the pooling layers don't really have adjustable parameters in them, so you may not want to count them as layers. So this kind of hierarchy exists in a lot of natural data. So for images, you have a hierarchy between pixels, and then pixels can be, if you take a little patch of 7 by 7 pixels and you ask yourself the question again, same question I asked before, among all possible combinations of 49 pixels, 7 by 7 pixels, which ones do you actually observe in the world? And the answer is actually a very, very small portion. Most of the space is empty. Most of the space is completely random pixels that you never see in natural images. Natural images occupy a small subspace of that. And so what that means is that you can encode a local patch of 7 pixels in some efficient way, because you can, if you find a way of encoding where you are on the manifold of possible things, or whether you are away from this manifold of natural things or not, then you have some sort of useful representation of that patch. It's not true if I take an image and I take 49 random pixels, then pixels that are far away are not very correlated with each other. They could take completely different values. Okay, whereas nearby pixels are very highly correlated, so the collection of pixels occupy a very small subspace. So, so I can take groups of pixels and arrange them, and the dominant patterns that I will need to be able to detect to kind of characterize what happens in a 7 by 7 patch are things like oriented edges. There's not much that can happen in a patch. Basically, it could be uniform, or it could be a slight gradient, or there could be an edge at an orientation. And so if you encode the edge direction, that's pretty much all you need to do. Okay? But we want an algorithm that's going to learn this automatically. Then those edges can be arranged in what's called textons, or motifs, or elementary textures. And then those things can be arranged in slightly higher level patterns, motifs. Those things can form parts of objects, and the parts of objects can form objects. Okay? So if each layer detects a conjunction of things that can occur in the previous layer, and then turn on for things that are interesting, that would be kind of ideal. This kind of hierarchy exists not just for images, but also exists for speech, from samples to spectral band to elementary sounds to subphones and phones and phonemes and words, for text, from characters to word groups, clauses, sentences, stories. So you have this hierarchy in a lot of natural signals, and deep learning is an attempt at trying to discover this natural hierarchy to things. Okay, I'm going to stop here.